Okay, so it's 12 o'clock sharp, and in the interest of time, we can go ahead and get started. I'm Claire Jantz. I'm the director of the Center for Land Use and Sustainability, and we are really excited to have Dr. Hawkins here today, who is a professor in the Geography Earth Science Department, to talk about a relatively recent commitment that the university has made to go net zero in terms of carbon emissions. One of the first steps in that process is to complete a greenhouse gas inventory. And over the past year, the CLUS has been working with Dr. Hawkins and an army of students. And we've also had a lot of engagement from staff across the university to calculate where all of our emissions are coming from. And so while Tim is presenting, there's kind of an army of people who've been working behind the scenes to do this. But Dr. Hawkins' expertise is in climate and meteorology. So we'll also be hearing, I think, a little bit about why it's important for us to make a commitment to go net zero. So without further ado, we will hear from Dr. Hawkins.
Well, thanks everybody, and thanks for being here. Appreciate it. So yeah, as Dr. Jantz said, talk today about the university's climate commitment and greenhouse gas inventory that we've conducted here on campus. We'll start though with a little bit of history, just to sort of put all this into sort of context before we get into sort of the details of what we're doing here on campus. So those of you, that's not gonna work.
Maybe click on the slide. And
then I've clicked on everything.
Yeah.
Oh, there we go. Nope, too far. There we go. Okay. All right. So yeah, let's just start with sort of the basics. And again, most of you have probably seen a graphic similar to this. If you're in class with me, I know there's a couple of you guys who've literally seen this exact same graphic. So these are global air temperatures over the last 150 years or so. This is the instrumental record since we've had a reliable thermometer record to measure global temperature. There's a variety of different groups that do these types of things, but they all come up with more or less the same numbers. And so clearly you can see we have our temperatures have risen over the last century and a half. The last 6 years have been the warmest 6 years on the instrumental record. The last decade was the warmest decade. The decade before that was the warmest decade. The decade before that was the third warmest decade. 2020 was the second warmest year on record. So you can see there's some interannual variability. These big spikes typically correspond to El Nino years, but the overall trend is towards a warming planet. Again, nothing that folks have not heard of before. At the local level, we can do some of the same sort of analyses. So this is Franklin County temperatures since 1895 to the present. And you're seeing that same sort of pattern. Here's the mean temperature for the last century or so. And you can see in the blue the trend towards a rising temperature. More interannual variability because it's a local place as opposed to a global average. But those same patterns still apply. And you can do this sort of analysis throughout the world and come up with more or less the same sort of values here. The cause, of course, for the most part, are greenhouse gas emissions, primarily carbon dioxide, but not exclusively. We can also talk about methane concentrations as well, nitrous oxide as another big greenhouse gas. And there are other processes involved, such as clearing of land use, land changes, clearing of land, primarily forest. And so there's lots of things going on, but the main driver are carbon dioxide concentrations and other greenhouse gases. You're looking here on the right at what we call proxy data. So the last 2,000 years worth of greenhouse gas concentration data coming from things like ice cores, deep sea cores. Those are sort of the main sources of our information for this type of stuff. And you can see the important part here is right about the time of the Industrial Revolution, 1700s, 1800s, these concentrations start to increase dramatically. This is sometimes referred to as the hockey stick, where this would be the blade of the hockey stick, and this would be the handle. You can see our current concentrations, especially of carbon dioxide, we're right around 413 parts per million. So again, it's not a lot. Take 1 million molecules, 400 of them are carbon dioxide, but the change is getting close to a doubling from pre-industrial conditions, right? Prior to the Industrial Revolution, we were around 275 parts per million. We're currently at 413. So again, these are proxy data primarily derived from non-instruments, but there's a pretty robust science around that. This is actually the instrument record. This is sometimes referred to as the Keeling curve, named after the person that first decided in the late 50s that, hey, you know, the physics on this is pretty straightforward. Maybe we should actually start measuring the carbon dioxide concentrations. And so again, you're seeing sort of that rise measured at Mauna Loa Observatory in Hawaii. You're also seeing the interannual cycle that corresponds to the photosynthetic cycle of primarily the northern hemisphere and the plants there. So clearly we have an increasing trend in greenhouse gases at multiple time scales. I think it's always useful to sort of look here as well. This goes back 800,000 years. So this is from an Antarctic ice core. Again, just to sort of put our current numbers in perspective, you hear people talk about there's natural variability in the climate cycle. We shouldn't worry about global warming because we just happen to be in a warm cycle at the moment. There's some truth to that statement, that there are natural cycles, and you can see them here in the methane levels in red, in the carbon dioxide levels in blue, in the temperature record derived over the last 800,000 years. You can see these things are obviously highly correlated, and there are natural cycles. This is basically the glacial cycle, right? So the ice ages and the non-ice ages are what you're seeing in here. But here are our current greenhouse gas concentrations, 413 parts per million, again, to scale, where historically we've been at around maybe 220 parts per million, pre-industrialization about 250 parts per million, and now we're at 413 parts per million. So way out of the realm of anything we've seen in the last 800,000 years, and certainly not due to these changes in orbital variations that cause the ice ages. Methane is even more dramatic, right? So again, you can fit an average line of maybe 500 parts per billion. We're at about 2,000 parts per billion. So again, maybe 4 times what we've been at any point during the last 800,000 years. So yes, there's natural variability. What you're seeing now is not part of that system here. And so the question then becomes like, okay, well, what do we do about this? And that's sort of the point of the talk today, but we'll just sort of lay in some background here. Thinking about where we're going in the future, right? So now we're thinking about climate models and projections of the future. So the most recent estimates that are coming out of reports that are like coming out like in the last month or so, you can see the historic past of where we've been, and then these are future projections of where the global average temperature is likely to be under a range of different, what we call, and I'll just skip ahead and then we can skip back, shared socioeconomic pathways. Our climate models work really well. There's a robust science around sort of assessing the quality of our future projections and how well they work. What we have not no idea, but what we don't have a great handle on is how people are going to behave in the future. So we model a variety of different pathways, and those pathways take into things like this is sometimes referred to as the green road. This would be a pretty big commitment towards sustainability, a electrification of our transportation systems, a lot of our infrastructure systems. The red is sometimes referred to as fossil fueled, and so we're going to continue burning fossil fuels. It might be economically prosperous, but it could be an environmental sort of big problem here. Again, we're looking at these different pathways with different carbon dioxide concentrations in gigatons of carbon dioxide a year. So we're talking about huge amounts. Depending on which pathway we choose, depends which temperature response ultimately is affected. The Paris goal, you've probably heard about the Paris Climate Accord. That set the goal for humanity to limit warming to 1.5 degrees with maybe an upper limit of 2 degrees. 2 of these scenarios keep us there over the next century. 1.5 degrees is probably pretty doable. 2 degrees is doable for a lot of people, but there's definitely going to be some island territories and countries that go underwater as a result of that from sea level rise. And so, you know, 1.5 degrees is sort of where we're trying to be as an ideal goal. You definitely don't want to be on this planet if it gets to that point for a variety of reasons, but that is not sort of where this should end up as from an ideal standpoint. That. Oh, we're doing this with 2 hands. What that looks like globally. So there's a couple interesting things. You can start to map this out. This is the thermometer record. So this is what actually has happened so far based on our thermometers. These are what the models say would happen under the same amount of warming. The fact that these maps look more or less the same is good. That means that the models are doing a pretty accurate job of capturing what really is happening. That little blue spot is kind of interesting as well. That's the meltwater coming off of the Greenland ice sheet, which is right there. And they made The Day After Tomorrow, if you're familiar with that movie, is about that blue dot right there. This is what it looks like at 1.5 degrees of warming, 2 degrees of warming, 4 degrees. Again, this is the global average. Notice that a lot of places, especially in the land masses in the northern hemisphere towards the poles, are in the 6 and 7 degrees of warming. To put those numbers in perspective, the last ice age was 5 degrees colder than we are. So we're talking about going 4 or 5 degrees in the other direction. So picture an ice age, the Great Lakes, a lot of geology in the Pennsylvania area, as a result of that last glaciation, go the opposite direction. And so that's sort of the extreme that we're talking about here. Precipitation patterns are likely to change as well. And the take-home message here, again, under different levels of warming, 1.5 to 4 degrees of warming, the take-home message, these patterns all kind of look the same, but essentially the wet areas are likely to get wetter. You see sort of the jungle belts in through here and the mid-latitudes where we're in a relatively wet climate, we're likely to get wetter. And then the dry areas, the world's deserts, sort of these middle 2 bands here, are projected to get drier. There's certainly some exceptions to this. The most notable one is the Amazon, a place that is normally pretty wet, drying out, and that could have really significant global implications. But a likelihood towards both more intense storms, depending on where you are, and the flooding and the results that go along with that. That's something we're likely to see here in Pennsylvania. But in other places like Arizona and Southern California, more drought under the exact same scenario. So you're warming things up, you're drying out the dry places, moistening up the wet places. And so you're sort of getting these hydrologic extremes, neither of which is particularly good. I think it's sometimes hard to get your head around a map like this and a set of graphs that are sort of at the global level. So sometimes thinking a little bit more local in terms that are a little bit more accessible, I think is useful. And so those that were in class with me this morning, I just showed this graphic. But I think it's a good way of thinking about things. So this is looking at Eastern Pennsylvania and Western Pennsylvania under a variety of different warming scenarios. So higher emissions, lower emissions, and different timeframes into the future. So thinking about sort of the far future under a more heavily polluting emission scenario, what we're saying is that in 2070 to 2099, 50 to 70 years into the future, that Eastern Pennsylvania will feel like Southern Georgia, and Western Pennsylvania may feel like Alabama or Mississippi. Obviously, those places are very livable today, but they're very different than Pennsylvania. And if you've been to Southern Georgia, you've got live oaks, you've got pine forest. You do not have the ecosystems we have out here. You don't have ski resorts. You don't have major dairy cattle production. And so all of those things would need to adapt. And the problem is you're talking about decades, and forests don't adapt over decades. And so that's sort of the issue that we're starting to deal with and think about. And if Eastern Pennsylvania feels like Southern Georgia, what does Southern Georgia then feel like as it warms? And what does that new climate start to feel like? And so putting it into those perspectives is I think, useful sometimes. Here's a little animation I put together of Cumberland County, right? So this starts in 1950 and runs out to 2100. And you're looking at the average July maximum temperature. So each day has a maximum temperature. Typically in July, that maximum temperature is like anywhere from, 80, mid 80s to maybe mid 90s. So that's just like one day. Now the average temperature, what we're saying, again, just ignore the mapping, just look at the color scale, is going to increase from say like mid 80s to over 100 degrees down in the valley by the time 2100 rolls around, right? So again, it's not that you can't live in that climate, but it is a radically different place. That if the average July temperature is over 100 degrees per day, what about the days where it probably is hitting 112, 115? That's like Phoenix high, right? So it's just a very different place than where we are now. And I guarantee you those trees are not going to be happy. And the cattle are not going to be happy, and the ski resorts are definitely not going to be happy, even though you're not skiing in July. But the same thing holds true in the winter months as well. All right, so that's like climate change 101. The question is then, like, what do we do about this, right? So how do we actually deal with this? And there's lots of people at lots of different levels thinking about this. At the international level, if you follow the news, you've probably heard of COP26. That's the big international climate conference that has just passed. If we're being honest about this, to solve this issue, it has to happen at the international level. It doesn't mean you can't do things at the local level, but there has to be something at the international level. So COP26 and these annual meetings, the goal of these meetings is to sort of figure out a way to deal with global carbon emissions at the international level. The take-home message from COP26 that just ended is, let's check back next year and see how things are going. So, they've made some progress. I don't want to totally dismiss it. I don't want to spend all day talking about it. But it's hard to get 200 countries to agree on anything, right? Never mind something that's going to have a major impact on their economy. The way COP26 or any of these international agreements would actually come to fruition is that each individual country has to actually do something. And what that means is passing laws, right? So in the United States, if you follow the news, the big thing that just got passed was this big multi-trillion dollar infrastructure bill, some of which is fixing roads and bridges, but some of this is designed towards climate resilience and some things that would help reduce emissions, electric charging stations for vehicles and things like that. And if you follow the news, you know that the next big fight is this Build Back Better, which is another multi-trillion dollar bill. And that has a lot more climate-based stuff in there that would really directly deal with the US emissions. If you follow the news at all, you know that the politics are just sort of poisonous in this country. Regardless of where you fall in the political spectrum, people do not agree. So that's where this becomes problematic, is this stuff needs to pass. And you've got equivalent stuff going on in Europe and Russia and China and South America and Africa. They're all doing the same thing nationally, and that all needs to then contribute internationally. It's really hard, and that's the problem. You start getting more local, this is where you have huge successes. And so some people have even made the point like, forget this, it's not going to happen, or at least it's not going to happen in the timelines that we need it to happen. And this is where we're going to actually make some progress. So businesses see this, right? A great example of this is electric vehicles. 5 years ago, would you have thought you could like easily drive an electric vehicle? I wouldn't. But like 5 years from now, I think it's probably likely. And 10 or 15 years from now, I don't think you're going to have a choice. There are already multiple companies. There's a Ford Mustang, right? Ford Mustang is making an electric car. Like, the paradigm has shifted when that has occurred, right? So that's sort of where we're sort of starting to see some of this action, because they can move at a pace that's a lot faster than a national government or an international agency. And at the local level, you can do a lot of these stuff. You're seeing local communities that have greenhouse gas inventories and climate action plans. At the university level, that's what we want to mostly talk about today. So we've made a commitment here at Shippensburg University, and we're just one of many institutions that have done this, because at this scale, we're able to do things that you can't do it nearly as easily, mostly because of politics at the state and certainly at the national level. So we'll talk a little bit about that today. So let's talk about the university's climate commitment. So what have we done as a university to sort of move ourselves sort of in a direction that we can be part of this solution here? In May 2020, Former President Carter, who has since moved on, but the commitment she signed is still very much in place, signed this commitment. And basically what we said is that by 2023, the university will complete a climate action plan. The two folks that were really involved in this are actually sort of sitting right here. So when I screw something up, let me know. But what we've committed to, not by 2023, by 2023, we're going to sort of have our plan figured out. But the plan is going to talk about how we're going to get carbon neutral. So how are we going to reduce our greenhouse gas emissions to zero? In order to do that, we need to know what our greenhouse gas emissions are. So we need to inventory them. That's going to be mostly what we'll talk about for the remaining part of this talk here. And then also part of that is going to be this community resilience planning, and recognizing the fact that no matter what we do, some amount of warming is already baked into the climate system, and that will have an impact. All right. And so dealing with those impacts, whether it's increased forest fire around here, I think the thing we're going to be dealing with is bigger storm events and therefore bigger flood events. And how do you, as a community, Shippensburg, Cumberland County, South Central Pennsylvania, how do you become more resilient to those things that we know are likely to be much more relevant in the coming decades? Again, as I said, we're not the only ones. This is just sort of a screenshot of the local region, the Northeast here. And you can see on here the other universities that have committed to. This is a university. There are similar types of commitments that can be taken on, that can be undertaken by municipalities and other organizations. But this is a university, academic higher ed. Can high schools do it? School districts?
I think it's higher ed.
Okay, so this is a higher ed commitment, the way it's designed. But you can see we're right here, this yellow dot. What do we got? Dickinson, Messiah, Gettysburg College, F&M, Millersville, right? So these are some of the local folks. Slippery Rock's out here, they're on this list. I believe Westchester is one of these black dots over here. So you can see there's a lot. The black dots are people that have committed to some sort of carbon commitment in terms of their overall emissions. The yellow dots are the folks that have also done the resilience part of this. Some of this wasn't available, so some of these black dots may turn yellow as well in the future. So there's a lot of people doing this. That's the take-home message. It is a multi-year process, and we've just sort of started this process. So we start with sort of thinking about who we are and just sort of a profile of the university, developing a task force to sort of move forward on this. We're currently in the assessment part of this, which is a big part of the greenhouse gas inventory. And then at some point we start assessing the resilience. We've had conversations about how to start that process. And by year 3 for us, that's 2023. So not that far away, we should have a plan, all right? And the plan will then be enacted over the next 4 to 7 years. And at some point you probably revise this plan and update it. But that's sort of the general timeline of how this stuff works. So again, it's not just, you can't just flip a switch and do something differently. You really need a process to go about this. Here on campus, we have an implementation team. So there's an overall climate action plan committee. And again, this includes the academic side of things, but it's a lot of facilities side of things, right? So a lot of the vice presidents are associated with this, at the provost level, a lot of the facilities directors, the people that are running and making this, it's basically a small city, the people that are making this small city work. As part of that, you've got sort of this resilience stuff that we've talked about, social change and green initiatives. So we've got a whole bunch of people that are in these different groups here that are all contributing to the overall climate action plan. So applied sustainability, that is sort of a lot of the academic side of things and what we might do on campus. And then we'll talk mostly about this inventory right here as part of this as well. So again, you can see administrators, faculty, staff, students are all involved with this. So if it's something you're interested in, I'd encourage you to talk to Dr. Jantz down here. She can hook you up in a way if you're interested here. We'll quickly talk about one half of this, all right, namely the resilience of planning, because that's not going to be the focus. This is the idea, as we've mentioned already, the ability to anticipate, prepare for, respond to hazardous events due to climate impacts, right? So again, around here, I think the thing we're going to be dealing with the most is bigger storms and therefore more flooding. You might have some heat-related events, heat waves and maybe hospitalizations and air quality that go along with that. But I think the big thing we're going to think about here from a resilience standpoint is flooding. And so there's a whole community task force that's developing. And so we have a partner, South Mountain Partnership. South Mountain, of course, is down here in the Michaud Forest. And so thinking about how we work with the local community to sort of build this resilience, assess our resilience, and then think about sort of how we move forward from that point. So that's a big chunk of it. That's like half of what we're doing. That's not what I'm going to talk about today. We'll let you deal with that later on, right? What I want to talk today is about this idea of actually getting carbon neutral. All right. So how do we do that? That's the goal, right? In order to do that, you actually have to inventory what it is that we do on campus. So the idea of getting carbon neutral would be taking this is our old coal plant that was used to generate steam heat and heat all these buildings. It is now the engineering building. So we've made progress on that front. We'll talk about where that heat is now coming from. And then, conceivably having a massive conversion to solar. This is not Shippensburg University on the right-hand panel. That's a wastewater treatment facility in Pennsylvania. But those are the types of things that we're talking about. So let's talk about where our emissions come from and what we do on campus. So the biggest source of emissions not the biggest source, let me back up. One source of emissions are what we refer to direct emissions. So these are things that we do on campus that immediately create emissions. The obvious things are burning fuels, right? The place we burn fuels are to chill the water for the air conditioners, which is what happens in this plant right here. This is right across this street right here is the spiritual center right over here. So right along the rail trail. We're burning fuel in our vehicles that are campus vehicles. Fertilizers have greenhouse gas emissions associated with them. And then a lot of the refrigerants and chemicals that are associated with the cooling of campus also are greenhouse gas emitters. So those are the things that we directly emit from and also have the most control over. It doesn't mean we can necessarily do a lot, but we do have direct control over them. Another big source, what we refer to as scope 2, are the upstream emissions. And this is in most places, in most cases, 100% purchase electricity, right? So all these lights, the computer, that is coming from somewhere. We are not generating that power on campus. In theory, we could, but most places don't. It's coming from a power plant that is transmitting it over lines like this. This is right outside of campus here on Rice Road, these big transmission lines that eventually make it to campus, right? And so we're paying for that. And by us paying for that, we are basically saying, go ahead and turn the coal-fired power plant on, and we are responsible for a portion of that power plant's emissions. Conceivably, that power plant in the future could be a wind farm, in which case we would be responsible for a whole lot less emissions. But right now, around here, it's mostly coal. There's some nuclear, there's a little bit of hydro, but it's mostly coal around here. But that's sort of starting to shift a little bit too. The final scope we talk about, scope 3, are what are referred to as indirect emission sources. So these are things that are associated with the campus environment, but not necessarily happening right on campus, and not necessarily something we're buying upstream like the electricity. So commuting is the most obvious thing, but our paper purchases and the percent recycled that our paper is matters. Just university and travel in general, whether it's conferences, for students and faculty and staff, study abroad programs, our wastewater, when we flush the toilet, that goes somewhere. It's our toilet water, so we're responsible for the emissions that come out of the treatment plant as part of that. Same thing with our trash, right? The solid waste disposal, that's the county landfill over there in the bottom right. And then also just receiving the electricity, as you step down the voltage from these big high voltage transmission lines, there's actually a fair amount of loss that occurs in there. So you're generating the power at the plant. It doesn't 100% get to the electric outlet. And so those losses are also sort of accounted for as part of this indirect scope 3. So those are sort of the big categories on this. So let's actually talk about what the university looks like in terms of these. Before we do that though, let's talk units, right? So I know students in my classes never like units. They just put a number up there and just leave it without a unit, but they're really important in this case. What we're talking about for the most part is metric tons of CO2, carbon dioxide equivalent, MTCDE, right? So everything you're gonna see for the most part in this rest of this presentation are metric tons of carbon dioxide equivalent. And the reason we talk about that is because not all emissions are carbon dioxide. In some cases, we're emitting nitrogen oxides. In some cases, we're emitting methane, especially if you have like a lot, like Penn State has to deal with probably a lot of cattle, right? And the methane emissions that are coming out. We don't deal with too much of that around here, but we do have some of those emissions. But we need to be talking about apples and apples. And so the reason we care is because each gas has a global warming potential. And we set a baseline of carbon dioxide has a warming potential of 1, right? Carbon dioxide is the biggest greenhouse gas, but one methane molecule has 28 times the warming capacity of carbon dioxide, all right? So it's got a different residence times. There's all sorts of details that go into this, but a single molecule is 28 times more warming. A single nitrous molecule is 265 times more warming than carbon dioxide. And one of these refrigerants here, this chemical right here, is almost 2,000 times more warming potential than carbon dioxide. So to have like all these numbers floating around, what we do is we take, okay, all of these things, we emit some of this stuff, but it's pretty little. So let's convert using these factors here, all of this stuff into what it would be in terms of carbon dioxide. And that's where you come up with carbon dioxide equivalent. Just to put some of these numbers into perspective here, context, the average US citizen emits about 18 metric tons of carbon dioxide equivalent per year, okay? So that sort of gives you a sense of the types of numbers we're talking about. So what does the university do? Well, we've sort of collected all sorts of data for the university to sort of assess this, and our emissions are basically 1,000 times more than the average person. That seems reasonable given how many more people are here. In fact, it actually seems pretty good given that, we certainly have more than 1,000 students on campus, but about 18 metric tons of carbon dioxide equivalent is what we emit. And you can see it's a pretty even split between scope 1, scope 2, and scope 3. It's about a third of each, not quite, but about a third of each. So it's worth talking about each of those things. If our ultimate goal is to reduce our emissions to take this number to 0, which is what the goal is, all right, you need to then tackle each of these 3 sectors. So let's look at them in a little bit of detail. Here are the scope 1 emissions, right? And so again, this is about 5,000 metric tons total. But what you'll notice is that the overwhelming majority of this is coming from burning natural gas, all right? And we're doing that in 2 places. We're burning it, let me get oriented here. We're burning it over here at the chilled water plant, the picture I already showed you. We're burning it there to provide basically air conditioning and water supply to the campus. And we're burning it at individual boilers in a lot of the buildings and in Kreiner Dining Hall to generate steam to heat the planet. Not the planet, to heat the campus. So we're burning natural gas. You can see much less significant are the transportation. So this is the fleet, right? These are the campus vans and all the other vehicles on campus. This is the refrigerants and chemicals, right? So you can see there's a lot less of that stuff. Very small amount, we're talking like a gallon or 2 of a refrigerant chemical to make the air conditioners work. And then we have 14 chickens on campus. And so you can't even see that slice here, but that yellow's right in there. So it's not something that we care about in terms of trying to solve the problem. This is the issue, right? The red slice of the pie. In terms of scope 2 emissions, I can't show you, I could show you a pie chart, but it would just be a red circle because 100% of our scope 2 emissions are purchased electricity, right? So we're purchasing electricity at the tune of about 6,600 metric tons. So that's obviously important. We don't have a ton of control over that, but there's some things we can think about in terms of how we might want to tackle that number. In terms of our scope 3 emissions, again, similar story. So it looks like we have equal segments, but within those segments, there's an overwhelmingly important part of it. In this case, our scope 3 emissions are due to commuting, right? So you can see there's travel, right? The green would be the travel. That's, going to conferences, study abroad. You can see our waste supply that's going to the landfill. That's also our wastewater. You can see a very small sliver associated with paper, bigger chunk associated with transmission losses. But the thing that matters is commuting, right? And if we break that down even further, the thing that really matters is student commuting, primarily not because students are like, worse at commuting. There's just more of you. There's significantly more of you than there are faculty and staff. And so on the tune of like 25 or 75% of our emissions under the scope 3, under that are, on the order of the student commuting. So if you think of like, how do you want to deal with this? we could have the biggest gains are going to be somehow reducing student commuting emissions, somehow reducing coal-fired generated electricity purchases, and somehow reducing the natural gas that's burned on campus to heat and cool the facility. Those are the huge slices of the pie. Getting those to zero is not an easy task. I would probably argue it's impossible, and we'll talk about how you deal with impossible in just a second here. Let's look at the emissions over time, because this is actually kind of an interesting story and gives you some sort of perspective on where we've been and sort of some hope for the future. You're looking at scope 1 emissions, right? So this is the stuff we're burning on campus or applying as fertilizer and refrigerants may be. But clearly, again, the key thing here is the on-campus stationary, right? The red is the biggest chunk, no matter what year you're talking about. In 2011, 2012, we didn't collect data, but we have pretty good data for the rest of the time record here, about 15 years worth of data. And what you can see is in 2014, this was the conversion of our fuel source, right? So historically, what we did, the engineering building right now on campus, right, at the main entrance to campus, that used to be a coal-fired power plant that generated steam heat for all of the campus. And then there were individual chillers in the building to generate cold water for the air conditioner. We flipped that in 2015 and now have, so by the way, this was this was coal, right? We now have individual natural gas boilers in a lot of the buildings that generate our heat, and a natural gas steam plant, a natural gas chilled water plant over here that's generating the water. When people talk about natural gas as being a transition fuel, this is why. This is what coal gets you from emissions. This is what natural gas gets you from emissions, right? So we're accomplishing the same thing with a different fuel, but it is dramatically cleaner. This will not solve the problem. If I thought that the energy companies really intended to use natural gas as a bridge fuel, I'd say go for it, because it's a whole lot better than coal. I'm not 100% convinced that the gas companies really want us to ever get off of natural gas, and they would argue it's not possible. But at some point, this needs to go away. That's a much harder lift, right? This was doable. It costs a lot of money, but it saves money. The gases were much more efficient. All right, so it saves money and it also dramatically reduces our carbon footprint. So there's sort of a win-win there. Here are our scope 2 emissions over time. And you can see not quite, again, this is 100% purchased electricity. And you can see those have fallen. They fell dramatically here. There was a big conservation effort where right around 2006, 2007, the university put in a lot of these motion sensors and automation that really just had the ability to shut buildings down on the weekend and at night the way they didn't used to be able to. And so you can see there's a big success right there, but that sort of has whittled off over time. I'm not actually sure what this sort of seemingly longer term trend is towards a little bit less purchased electricity. It's probably efficiency, but I don't know the details of that. But you can see we still have a long way to go. At some point, we got to keep these lights on. And how you do that is a challenge. Here are our scope 3 emissions over time. These haven't really changed a whole lot. They kind of ebb and flow with the student population. But again, you're seeing, sort of those commuting numbers are sort of driving it, and those haven't changed. We actually, part of this is the fact that you can't survey students, or we haven't surveyed students on like a monthly basis, right? So we are actually in the process of putting together a survey. So I suspect, I don't know which way it's going to go, but I suspect 2021 numbers will change somewhat from 2020 based on the current survey that we're going to put out relatively soon. So if you see that, do that, and that would be helpful for most people to take that survey. So that's how things have changed over time, or in this case, not a whole lot. Here are our total emissions over time, all right? And so again, what you're seeing mostly is that scope 3 and scope 2 haven't actually changed a whole lot in terms of the size of the stacked bar there. But what has changed a lot is the scope 1, right? So this was the conversion from coal to natural gas to primarily accomplish our heating and cooling. That was a big win. I'm not 100% sure where the next big win is going to come from. That's the whole point of the climate action plan, is how do you get this number to 0, right? Because we're not converting from natural gas to coal, right? We already did that conversion. So what do we do? You know, that's what we need to think about here. Some institutional data over time. You can see the green is the size of campus. It's increased a little bit with some construction. So we've gone from just under 2 million to maybe 2.4 million square feet in terms of building size. So the buildings we've got a few more buildings, which means we're probably using some more energy. You can see the budget. This is just all over the place. It's sort of at the, you know, the whims of the state legislature. So I'm not even going to pretend to try and interpret this red line, but we do know how much money the university spends, and it's on the order of hundreds of millions of dollars per year. And then we also know how many students there are. And you can see the enrollment has decreased. And, you know, before you say, why is everyone leaving my university? They're leaving every university. There's just literally less students in the state of Pennsylvania because there weren't as many babies born. And actually, it's a national trend. So you're seeing this around the country. Everybody's dealing with sort of decreasing enrollment numbers. But, you know, as your number of students decreases and the size of your buildings increases, you know, what does that mean from an emission standpoint? You can normalize these data. So you can take your emissions and divide them by the number of students, divide it by the square footage of buildings on campus, divide it by the dollars spent. These graphs actually aren't all that interesting, but I'm making the point that you can normalize these things and talk about what are your emissions per 100 students, per 10,000 square feet, per $1 million. And so it allows you to sort of compare things year to year. That could be useful to account for sort of big changes, and maybe, you know, if you built a new building, you know, maybe you're using more energy, but you might actually be better and more efficient given the size of the campus. Or as your student population ebbs and flows, you can sort of account for that. So these graphs don't actually look all that different than sort of the overall numbers, but what these graphs allow you to do is compare to other universities that might have radically different sizes, right? So our, I don't want to say competitors, but the people that we like to always compare ourselves to are the other PASHE schools. And so we're able to access Millersville, Slippery Rock, and Westchester have all part of the same commitment that we are. The most recent numbers for which all four of us have is 2017. So these are the actual emission numbers. These are not normalized by either the area, the size of the school, or the students. And you can see, compared to our competitors, we are the lowest emitter, right? The story gets more interesting, though, when you start comparing those numbers. Millersville, these are actually in order pretty much from, these three are about the same size square footage. Ship and Millersville have about the same number of students. Slippery Rock has a little bit more, not a lot more, but a few more. And then Westchester is just bigger, students-wise and area-wise. So they're just the biggest by far. So, you know, this number is actually reasonable given who they are. When you divide the emissions by the size of the school, all of a sudden Westchester looks really good, right? Because they're just a bigger place. When you divide by the number of students, Westchester's the best, right? So on a per student, or in this case, per 100 students, Westchester has a smaller carbon footprint than we do, right? So one of the things we're going to do as a climate action committee is to look at some of these sister schools, look at other universities, see what they're doing, and how do you actually get to this spot. So the logical question that you're hopefully all asking is, how do you reduce your emissions? How do we actually go about doing this? So scope one, that's the stuff we burn on campus mostly, right? The big thing are those power plants, right? And the boilers in the building that are providing the steam, heat, and the air conditioning. I'm not going to pretend to have an answer to this, but the types of things that could potentially work are solar thermals. This is not solar electric, right? You see the solar panels that generate electricity. This is solar thermal. You could use this to generate electricity, but you can also use it to generate heat. So solar hot water, there may be some uses for that. You may electrify the heating systems and the cooling systems and run those things through electrification, and that electricity could conceivably come from solar power or wind power. I guarantee you the university is not building a solar field anytime soon. And so how do we deal with that is going to be sort of one of the big things we need to tackle. A little bit easier to do. My guess is this will probably happen at some point as vans and other campus vehicles start to get, you know, outlive their useful life. We may start replacing these things with electric versions of these things, which have a significantly lower carbon footprint, depending on where the electricity comes from, right? If it's coming from a solar electricity, then that's obviously better than coal-fired electricity. So again, these are not necessarily what we're going to do, but the types of things to start thinking about. In terms of scope 2 emissions, remember, this is the electricity. This is what's keeping the lights on in this building. The places that are most, or the things that we're most likely to do is either build an on-campus solar facility. Again, I don't know, Russ, you probably have a better sense of the likelihood of that happening, but I think it's probably relatively low. Yeah. Much more likely is at some point we purchase our electricity where we know it's from a solar generation facility. And I think there's been conversations about pooling multiple schools together, because that'll make the make it worthwhile for the generator. And as a university, we could probably get a cheaper rate on that. So there's sort of these sort of bulk purchases that are being discussed. We did that with wind maybe a decade or 15 years ago. So yeah, we could also purchase wind as well. So rather than purchasing coal-fired electricity, we could purchase renewably generated electricity. In terms of your scope 3 emissions, right? These are the indirect. Again, commuting. See how many of you get my reference here in the upper right. I may be dating myself if you know who these people are here. But carpooling, I mean, these are the types of things we're talking about. Carpooling, electrifying the bus fleet. Again, riding bikes, electric cars. We have a lot of students driving to campus. How do we deal with that, right? And, you know, we could have all the electric buses in the world, but if nobody gets on them, it doesn't matter, right? And so those are the types of things you have to start to tackle. And we are a very commuter-heavy campus. We got people coming from Hershey to Hagerstown, and everywhere in between. And so, how do you deal with that as a university here? Hopefully, it's come across that this is sort of a difficult issue to go carbon neutral. Say I'm carbon neutral. I would argue is pretty much impossible. And people that say they're carbon neutral are doing something else. And the main thing that they're doing is purchasing carbon offsets. All right. And so this gets it. We could do a whole talk about this. We'll do one slide on it. All right. The idea of a carbon offset is, I would argue, it's probably not impossible, but it's nearly impossible, depending on the size of your organization, to actually be 100% carbon neutral. All right. To do that, to get and to be able to claim carbon neutrality, usually what people do is they purchase an offset. So in other words, Shippensburg University says, we're going to reduce our emissions from 18,000 tons down to 5,000 tons. And you know what? We just can't do any better than putting out 5,000 tons. So therefore, we are going to spend tens of thousands of dollars to help build a wind farm that will generate enough electricity without carbon emissions to offset our 5 tons. If you just sort of think through that process, you can imagine all sorts of places where that whole concept could go wrong. Right? Some other things people do, planting a forest, right? You go plant a tree, those trees absorb carbon, therefore it offsets your carbon emissions. A much more thornier one is you pay somebody to not cut a forest down. You can do that. If you want to go take an airplane flight and you feel guilty about flying to California, you can pay somebody through a market to not chop a tree down in the Amazon, and you feel better about your flight, but I'm not convinced that you actually helped the problem. At the end of the day, you can't buy off, the whole planet can't buy offsets. Somebody's got to actually reduce the emissions at some point. And that's where this starts getting thorny, right? Some issues along with this, right? This is a graphic that's sort of based on, you know, a travel, right? So you produce emissions with your trip, you can help build a solar farm or plant some trees, and that would reduce that, and you sort of keep the scale at neutral. But like, have you actually made the system better? Like, how do you know that those forests was going to get cut down if you didn't pay for it, right? Will it last? Just because they didn't cut it down this year, does that mean they're not going to cut it down 50 years from now, in which case it doesn't matter? How do you check that? I mean, how do you know that that solar farm is doing what it says it's going to do? And ultimately, again, it's all just a Band-Aid. At some point, you actually have to reduce the emissions, not pay. If we all pay somebody else to reduce the emissions, it's just a big circle of everybody chasing each other's tail, right? At some point, it doesn't work. Somebody's got to actually stop, right? And so that's sort of the issue that we're dealing with here. So my guess is Shippensburg University, as part of their climate action plan, is going to propose that we buy offsets. But we need to be smart as to how we actually do that. And who knows, if we plan to buy offsets in the year 2040, maybe by 2040, we'll have a better plan. But that's sort of the state of where we are at the moment. So that's what I got. So I think I'll stop there. If you're interested, oops, that's the wrong click. If you're interested in some of this stuff, there we go. There's my contact information. Dr. Jantz, who's sort of leading this, could certainly help. And then some of the folks that work at CLUS are listed there as well. Marianne's right down here in the front. So if you're interested in these ideas, you want to participate, I encourage you to reach out. And at this point, I will shut up. And if anybody has any questions, we can certainly do that.
We have about 5 minutes for questions. We have about 30 people, 25 people on Zoom. So you Zoomers can submit questions through the Q&A, but we also have a number of people here in the audience. If you all have any questions, please chime in.
Perfectly straightforward.
No questions. So most of you all here look like in the audience, look like your students. And so, except well, even Dr. Hedberg looks like a student. A little overdressed for a student, but what were you feeling when you saw that student commuting was like the biggest part of the scope?
I mean, I know me personally, I'm a commuter now because like me living on campus was $13,000 versus living off campus is like $5,000 a year for me. And I walk. I know some people are gonna drive, but I think the cost of living.
Yes. So as Dr. Hawkins said, in the spring semester, January, February, you all should be looking for an email blast and all kinds of social media. You're going to get blasted with a chance to respond to a commuter survey. Staff and faculty will be responding to the same survey as well. And one of the questions on that survey will be, would you be willing to participate in a focus group? Like a short meeting, we'll feed you pizza, but those are the types of things we want to hear about. Like, if you're commuting, what can we do to change your behavior? Is it decreasing the cost of housing on campus? Is it providing more electric vehicle charging stations? Is it providing incentives to walk instead of drive if you live that close? So hopefully a number of you will choose to participate in the focus group so that we can learn more about how we can help address that piece of the puzzle.
Other questions or comments?
That's good. Why do you think it's impossible to actually get to zero?
It's not impossible. I think because I don't see the university spending the money to actually do it. So I mean, that's really what I mean. It's not that it's impossible. It's that at some point you sort of hit a law of diminishing returns where they're not going to spend the money to generate to build a solar farm that can actually do all the things that we need to do. So you could, yeah, in theory, you could absolutely do it. I don't know if some of you went to the talk earlier from Carl Hosker. He basically proposes, and I don't know if I agree or disagree, but it's actually not in society's best interest to 100% get rid of fossil fuels. We should keep it at like 5% of our energy supply or some really small amount, because that would then allow us to not spend so much money, make an unattainable amount of money on alternatives. So that would sort of be mine. It's a money thing. A money thing and a willingness. For a technology, you could do it.
We have one question from Luke on Zoom about whether or not campus is, if we're currently using energy efficient lighting, and if not, there could be some energy savings there.
Yeah, so the short answer is, are we using energy efficient lighting? The short answer is I don't 100% know, but part of that electricity reduction in the scope 2, That's what happened in like 2006 to 2000. They went in every building, changed out every light bulb, installed timers, installed automation systems. So I think there's probably still some more gains that could occur, but I think we did a lot of that stuff about 10 years ago. Or so.
Yeah, back then, I think we would have been transitioning more to fluorescence and contact fluorescence.
Yeah.
And now we can make a transition to LEDs, which are even more efficient.
Yeah.
So I don't know if we're gonna whole scale transition to LEDs like we did with fluorescence, but you know, as we have to replace light bulbs, let's go and it's the most efficient.
Yeah.
So we'll continue to see like slight gains in efficiency as we kind of go through time, but it's unlikely that we're going to see any more big jumps, particularly in scope 1 emissions.
Yeah, I mean, for scope 2, the big jump you would see is if we purchase solar electricity or purchase wind electricity as opposed to purchasing coal-fired electricity.
Okay, well, thanks everybody for coming, and I hope that that's something that we will hear a lot from you all. Hopefully there's interest. If you're interested in serving on any of our committees, if you're interested in helping to write the plan, you know, we want as much student engagement in this process as possible. So please reach out to me or to Marianne or to Tim or to Russ. Any of us would be able to point you in the right direction if you really want to get more engaged.
Thank you.
All right.
See you guys.
Thanks so much.
Thanks.